A renowned Nobel laureate warns us the James Webb Telescope has just discovered something strange in the universe, and we may not even be ready for the changes that are coming. The latest discoveries pose serious problems for our science. It's getting crazier and crazier because, yet again, James Webb has discovered a completely new phenomenon that is turning our physics textbooks upside down. Astrophysicist and Nobel Prize winner Adam Rees has long suspected that the scientific community is heading for disaster. Researchers report piles of unsolved puzzles that are growing every day. Can we still get to grips with the situation, or is our science at an end? Adam Rees is probably one of the few researchers who is keeping a cool head these days. Since the launch of the James Webb Space Telescope, nothing is as it used to be. The universe is probably much older than assumed. Galaxies have formed much faster and quite differently than all our predictions, and our cosmos may not be expanding from a single point. What happens now if dark matter is possibly still a mistake and James Webb is already presenting the next picture of inexplicable phenomena in the cosmos? Adam Rees is one of the leading experts in the field of research into the expanding universe. His contribution to the discovery of the accelerating expansion of the universe revolutionized our view of the expansion of the cosmos and was one of the cornerstones of the Hubble excitement. Rees welcomes the telescope's latest discoveries because he knows from his own decades of dedicated work that our cosmology is flawed. He was involved in surveying the cosmos and using supernovae as standard candles for the first time. In this context, standard candles are something like cosmic scales that scientists use to measure movements and distances in the universe. Using supernovae as a yardstick, astonishingly precise measurement results could be achieved. But one problem remained. Rees and his team found that the expansion of the universe was increasing regionally instead of decreasing. In the course of their work, another phenomenon became apparent as Rees's measurement results differed significantly from those based on the redshift method. This should not really be the case. Today, we know the differences in the measurement results as the Hubble voltage. Rees's work was so phenomenal that he was awarded a Nobel Prize in Physics in 2011. Together with his colleagues Saul Perlmutter and Brian P. Schmidt. In fact, he received the award for the discovery of the accelerated expansion of the universe. Rees and Schmidt are members of the High-Z Supernova Search Team, which is researching techniques to refine the measures of distance in the universe. Perlmutter, on the other hand, came to the same conclusions at around the same time as part of the Supernova Cosmology Project. They observed Type Ia supernovae, very bright exploding stars that serve as reliable indicators of distances in the universe. These observations provided the surprising evidence that the rate of expansion of the universe is increasing rather than decreasing due to the gravitational effects of matter in the universe as previously thought. Bad mistake, the isotropic universe. The biggest crisis in modern science was slowly brewing, and now the bomb has exploded. Instead of answers, astronomers and cosmologists are constantly being served up new puzzles and shocks these days. Now the concept of an isotropic universe is also on the brink of collapse, and with it, one of the fundamental pillars of our cosmology. Isotropy assumes that the universe looks the same in all directions regardless of where you look at it from. This assumption is a fundamental part of the cosmological principle, which states that the universe is homogeneous and isotropic if we look at it on a large enough scale. For example, the cosmic microwave background radiation pattern looks uniform everywhere, and large clusters of galaxies are also distributed almost uniformly across space, at least that's how it used to look. Scientists then turned these observations into basic mathematical rules to simplify scientific descriptions of the universe. But this may have been a stupid mistake. The observations of Adam Rees and other scientists researching accelerated expansion have initially confirmed the isotropic model, at least in part, because the measurements of supernovae have shown consistent results with regard to the rate of expansion. This means that there appears to be some kind of isotropy. However, the expansion is much faster than it should be according to old physical assumptions. The end of dark energy. It remains exciting in science. In order to understand the puzzle of the new cosmology, we need to take a closer look at dark energy. The exact nature of this energy is still unknown, but its existence and properties are crucial if we want to understand how and why the universe expands in an isotropic way, and why researchers came up with the current standard model of cosmology. Dark energy is a hypothetical form of energy that could be present anywhere in the universe and very likely plays a key role in current theory about the expansion of the universe. It's thought to be the driving force behind the accelerated expansion of the universe. By acting against gravity, it pushes the cosmos apart. In current cosmological theory, dark energy is responsible for about 68% of the total energy content of the universe. Here you can already see a problem. Scientists blame almost 70% of the energy processes in the universe on an energy whose existence has never been proven. An important element supporting the existence and properties of dark energy up to now was the observation of Type Ia supernovae, as carried out by Adam Rees and colleagues. The accelerated expansion observed here could not be explained without the effect of a large repulsive force. Further evidence that this mysterious energy really exists was provided by the cosmic microwave background radiation and other large-scale structural studies. However, recent observations by the James Webb Space Telescope have now shaken the concept of dark energy. The JWST can observe the early universe in a level of detail that was previously unattainable. Even the first precise observations revealed structures and objects that are older and more developed than they should be according to the standard model of cosmology. These observations could indicate that the universe may have expanded even faster or originated at an earlier time than previously assumed. All these results indicate that we have not yet understood some crucial elements and forces in the cosmos, including dark matter and dark energy. It's very likely that we are now facing a complete revision of the standard cosmological model. But we are not ready for that at the moment. We can't come up with new theories because we don't have enough tangible information about what's new. Will we find the answer in the world of quarks? So, the revolution in our worldview will have to wait a little longer. Only when Webb provides us with more images and researchers make even more incredible discoveries will we be able to piece together a new picture. That may take time. In the meantime, researchers around the world are searching for answers that are already available. David Gross is another scientist who welcomes the crisis and sees it as an opportunity. Gross points out that the answers to the great mysteries of the universe are not hidden in the macrocosm, but in the microcosm. The renowned theoretical physicist is an expert in the theory of strong interaction and string theory. He is also one of the Nobel Prize winners and received the award in 2004 for the discovery of asymptotic freedom in the theory of strong interaction. The discovery was fundamental to understanding the behavior of quarks, which are the basic building blocks of protons and neutrons. These particles are the main actors in the standard model of particle physics, and they are the basis of everything we can see and measure in space. Consequently, the basic structures and principles of the macrocosm must also have counterparts in the subatomic realms. The concepts that Gross helped to develop deal, among other things, with the events shortly after the Big Bang. Realizing that there were no stars and no objects in the universe at that time, for hundreds of thousands of years, there was only an extremely hot primordial soup in which particles flitted freely through space without forming bonds. Before the Big Bang, there was presumably only a kind of quantum fluctuation in which all forms cancelled each other out in such a way that, from a physical point of view, they amounted to zero. With the Big Bang, this quantum fluctuation fell apart, and particles packed with charges and forces shot into an otherwise empty space. These particles later became stars, galaxies, planets, and life forms like us humans. Is Gross right when he says that these particles are the answers to all the questions? Probably, yes. But how do we study the behavior of particles that were in space 13.8 billion years ago? Among other things, researchers use the cosmic microwave background radiation. This is considered to be a fairly accurate reflection of the events shortly after the Big Bang and has probably not changed much since then. However, quantum physicists and classical physicists do not quite agree on how to interpret this imprint of the early days of the universe. At the moment, the situation in science is that quantum and particle physics cannot be reconciled with traditional cosmology. The findings from the world of formed matter do not fit with quantum physics, or rather the binding link is missing. David Gross is convinced that this bridge can be found in previously unknown particles and forces. He was one of the researchers who worked hard to reach a consensus between the disciplines even before the debate triggered by James Webb. As co-author of string theory and in a coherent unification of quantum mechanics and general relativity, he was keen to close the gap between the two worlds and disciplines of science. Gross's work on asymptotic freedom describes how quarks behave at very high energies. This is fundamental to understanding the early universe shortly after the Big Bang, when energies were extremely high. His theories can clarify as yet unclear aspects of the expansion of the universe. However, there is some controversy among scientists, as the thesis of string theory is too far-fetched for many classical physicists. David Gross suspects that the answers to all unanswered questions lie in the quantum fluctuations within the microwave background. The CMB fills the entire universe and can be found in all directions around us. The Cosmic Background Explorer satellite, which was active from 1989 to 1993, was the first to notice tiny fluctuations in the temperature of the radiation. From 2001 to 2010, the Wilkinson Microwave Anisotropy Probe researched to find evidence of the Big Bang in these fluctuations, and most recently, the Planck satellite provided one of the most detailed maps of the CMB. However, there is still disagreement among researchers as to how this data should be interpreted. While some claim to have found the necessary evidence for the Big Bang in the CMB, others see the data as evidence for collisions with parallel universes and the existence of the multiverse. Become a subscriber now and be part of every new video.